Hey class, it's Mr. Hofstad. Here we are with our final unit of Physics 30. It's an interesting one for sure. This is going to be a lot of fun. Learn a lot of things that you probably didn't know about atoms and nucleus, different reactions. So, as always, we got our fun little cover page cartoon. This time we have a couple of old decayed particles reminiscing about the good old days when they were radioactive isotopes of uranium and how everything was downhill from there. Kind of a play on decay reactions, which we'll cover next class. So hopefully you had a chance to watch the other two videos in the materials post I put, the examples and the crash course video. Those ones are very good, very informative, and I'm just going to quickly go through the notes, but I encourage you to watch those other two videos before this and maybe work on the homework after this video. That's how I would do it anyways, but do whatever you feel like. Alright, so we have with lesson 1, we're just looking generally at what nuclear physics is. This is a more modern physics than we've been looking at. Well, I think we finished off with the 1920s at the end of atomic physics, so a little bit back from then. But hopefully all of you have some knowledge of our different subatomic particles, electrons, protons, and neutrons. This was kind of theorized by Rutherford in this period, right, using an experiment. They were able to identify these two different subatomic particles, protons and neutrons. They were quantized, again, like the word quantum. We're thinking about discrete groupings. Yeah, almost like the integers of the physics world. They can't exist as half particles or any fraction of a particle. They are quantized. They have to be whole numbers, whole particles. And this might be a new terminology. We call these in physics nucleons. So protons and neutrons are both classified as nucleons because they exist in the nucleus, right? Nucleon, nucleus, very close connection there. So this are all the three parts that we already know about an atom. And we're going to keep adding parts onto that as we go. So electrons have essentially no mass. Again, if you look at our data sheet, we can find that atoms have a mass to the order of magnitude of 10 to the negative 31 kilograms, which is smaller than our unified atomic mass unit. So they don't contribute to the atomic mass of an atom at all. So 0 for that with an electron. They do have a charge, -1, where protons have +1 and a unified atomic mass unit of 1 as well. Neutrons have no charge, they're neutral, right? And they have, in this course's purpose, the same atomic mass as a proton. The real world, they're slightly different, but we can kind of simplify it and look at it less specifically and just call them both 1. So this U means unified atomic mass unit, and this word unified is important, right? That's where we get the U from, and that just means that it's the atomic mass of a proton or a neutron when they are unified. So they need to be unified inside the nucleus. So when they're not unified inside a nucleus, they're going to have a different mass than this, which we'll see shortly. So this is when they're bound up, when they're undergoing strong nuclear forces with one another, and it's a slightly smaller mass than we have when they aren't unified, when they're separate protons or neutrons, right? So one unified atomic mass unit is approximately equal to 1.66 times 10 to the negative 27 kilograms. This is given in our data booklet, as is the separate mass of a proton and a neutron. So you can find that all on the physics data sheet. All right, this is a nice review of chemistry. We have nuclear notation. So here we're looking at sodium 25. Here's our notation we're going to be using. So we call the mass number the A for some reason. I don't like and I don't understand why we do this. For me, I would think A should be atomic number and maybe Z would be mass number. That's not how we do it, right? Just remember that A is before Z, so it goes on top, and Z goes on bottom. So this is kind of the standard notation, where A is the mass number, which is the total number of nucleons, which are, of course, our protons and neutrons. And this is going to be measured in unified atomic mass units, RU, 1.66 times 10 to the negative 27 kilograms. And the atomic number is only the number of protons. So we can find the number of neutrons by subtracting A minus Z, because, right, nucleus, or number of nucleons, is protons and neutrons. And if we're looking to solve for the number of neutrons, we just need to subtract the protons, which is the atomic number. So the element type is determined by the number of protons, and the charge of the nucleus is determined by the number of protons as well, because neutrons, are neutral. And we take the charge of a nucleus in our E units, which is our elementary charge. So the same charge as one electron, one proton. Okay, so in the example in Mr. Holloway's video I posted, we looked at uranium 235. So I encourage you to go through that example video and break that up to find the number of neutrons, protons, and nucleons, right? So using the isotope number and the atomic number of uranium, right, we can calculate all three of those. So an isotope, again, a lot of review. I think these were even introduced in Science 10 way back when. But an isotope is any element with a different number of neutrons. So they are the same element because they have the same number of protons, right? If you have the same number of protons, you will be the same element, but we have different numbers of neutrons. So a different atomic mass, or a different mass number. So they'll have the same chemical properties because they're the same element, but they'll have different nuclear properties, which is more of a new idea for us. This idea of stable versus radioactive. So different isotopes will have different nuclear properties. Some will undergo decay reactions when they're radioactive, and others are at a nice stable or ground state where they can exist happily forever. All right, strong nuclear force. This is very important. This is one of our 4 fundamental forces in physics. It's only found inside the nucleus, and it's what's allowing the protons and the neutrons to, especially the protons actually, to be held in place, even though they have this repulsive force, right? If you have 2 protons within the same nucleus, they're going to naturally want to repel each other because they're two positively charged particles. So our electrostatics unit tells us that like charges want to repel, but instead of repelling, they are held together in place inside this nucleus with this strong nuclear force. All right, so this force can only act over a very short distance, right? This order of femtometers, 10 to the negative 15 meters. And it's what's really holding the nucleus together. So this is the strong nuclear force holding the nucleus together. And it's an attractive force, obviously, between any pair of nucleons, right? Neutron, 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 proton, proton, proton. All of these nucleons are being held inside of the nucleus by strong nuclear force. So it will only work over very short distances, but when they are actually that close together, it is indeed the strongest force in nature. You don't want to mess with strong nuclear force. As this distance increases, as we get further away, it decreases dramatically. So they really need to be close together. Otherwise, you'll see this exponential decrease, actually beyond exponential. So you need to have really close contact between these particles for strong nuclear force to occur. All right, now getting into my man Einstein. The nuclear mass defect idea is pretty groundbreaking because instead of thinking about the duality of waves and particles with light and other matter, we're now looking at this mass energy equivalence to explain this understanding that scientists and physicists have, where the total mass of any stable nucleus will always be less than the sum of its parts. So if you have these separate protons and neutrons and you find their mass, they'll always have a greater mass when they're separate than when they are inside of a nucleus. So that difference in mass between separate protons and neutrons is what we think of as our mass defect, right? So we need to have our separate protons and neutrons versus our unified. Right, so when they're inside of a nucleus, they're unified, and that's when we're going to be using our unified atomic mass unit, our little u. And when they're separate, we're going to be using the mass found on our data sheet, where so this one would be our 1.66. Sorry, 1.66 is our unified mass times 10 to the negative 27. And our separate protons and neutrons, when they're not in a nucleus, when they're just floating around in space, is our 1.67 times 10 to the negative 27. So we are slightly heavier when we're separate. And that heavier separate part, right, gives us this difference in mass, this mass defect. So we need to find the total mass of our protons and neutrons that are separate using the mass of the individual particles, 1.67 times 10 to the negative 27, and the actual nuclear mass, which is coming from our unified atomic mass number, 1.66 times 10 to the negative 27. So we'll always have a greater mass of separate particles than unified or bound in inside the nucleus particles. And this was explained by Einstein in 1905 when he proposed mass was another form of energy. This is very weird, very backwards. Don't break your brain too much by obsessing over this. None of us can match the grandeur that is Einstein's mind, but take it as it is. Maybe down the road you'll have an epiphany and this will all make perfect sense. Let me know, even if it's years down the road, when you have that aha moment. I'd appreciate the enlightenment for sure. So this lost mass, or inner mass defect, isn't actually disappearing into space, right? Instead, it's going from mass as we think of it into this strong nuclear force, energy. So it's converted from mass into another form of energy, that binding energy inside the nucleus. So that other form of energy is this nuclear binding energy. So you can calculate the equivalent energy from the mass defect using Einstein's and honestly physics' most famous formula, E equals mc squared. It only took you 3 years of high school physics to get to this point, but go ahead and give yourself a round of applause or a nice pat on the back, whatever it'll be. You made it. You are now learning about E equals mc squared. So this mass in E equals mc squared is actually the mass defect found by comparing the separate protons and neutrons and the bound protons and neutrons in an atom or inside of a nucleus. And we're going to multiply it by the speed of light, 3 times 10 to the 8 meters per second squared, as found in our data booklet, data sheet. And when you multiply those two guys and the speed squared, we will get the energy in joules, because joules, of course, when broken down, become kilograms meter squared per second squared. All right, so as a result, we have this new principle of physics, the law of the conservation of mass energy. It's more general than the conservation of mass. It's more general than the conservation of energy, because now we have this duality between mass and energy, where mass can be looked at as energy and energy can be looked at as mass, all tied together using Einstein's most famous formula, equals mc squared. So this will be referred to on our data sheet as the principle of physics number 6. Law of conservation of mass energy. And that's when you finally get to play with Einstein's formula. All right, last little section before you get to work on the homework. We have the nuclear binding energy, which is the equivalent energy associated with the mass defect. Again, found using this formula, E equals mc squared. So the mass that is lost when we have the protons and neutrons bound inside the nucleus is turned into this nuclear binding energy. So the nuclear binding energy is what we are accounting for the mass defect with. So it can also be thought of as the minimum energy that must be put into the nucleus in order to completely break it into its components, protons and neutrons. So if you want to split apart an atom or a nucleus, you'll need to inject this amount of energy, the binding energy, which is equal to the energy released when that nucleus originally formed in the atom. Very similar kind of thinking to our hydrogen atomic spectrum and the energy absorbed by photons of the exact energy, and the energy ejected as electrons change their states. Right? I see a parallel there. If you don't, forget I said anything about that. But yes, that's all I got for you today. If you have any questions about nuclear physics, give me a shout via email or whatever. Yeah, that's really the only way you can reach me. Good luck with this. Do some deeper investigations if you want. This is a super exciting branch of physics. And if you need a distraction from what's going on in the world right now, what better way to take your mind off of it than to really dive into nuclear physics. So good luck with the homework, and I will see you all next week with our nuclear decay reactions. Lots of fun. See you guys. Good luck.